Hey guys, this is walkthrough the gym term 1A, first in a three-part series. Goal of these walkthroughs is just to get through the exam, see how I think about it, so that hopefully you guys have an easier time and you can see how I solve these. Um, this one in particular, so 1A, this video is going to be a lot longer than the other two, just because not only do I want to get through the material in the exam, I also want to do a little bit of review, just so everyone is on, has a baseline of what they should know. Nothing too crazy. We're not going to spend like an hour on review, but we'll spend a good chunk of time on review. The other two videos won't. So B and C will just go straight into the midterms and complete them and whatever else I want to do. So that's about it. But for this one, we'll take the time to review the reactions after I finish talking, just so that we are on the same page on what we need to know. In general, I would recommend you at least get through 1A and 1B. 1C is a little hard, not gonna lie. So it's okay if 1C is not your favorite. I kind of wrote that as if I would write to exam for the class, that's what it would look like. So I would highly recommend for those of you on a crunch for time, make sure to get through 1A, get through 1B. 1C is okay. You can omit that from your study plans. That's totally fine. Anything that I think is important at 1C, I'll make sure to talk about in 1A, 1B anyways. Okay, cool. Well, with that being said, let's just get right into it. So let's, before we even get to the reactions, let's make sure we know all of them. Let's do a little bit of a mini review. Okay. But this midterm one's going to be all about the acyl derivative, right? The carboxylic acid and its derivative family. So we start with chapter 19 that talks about carboxylic acids reactions. And so first reaction you learn is, hey, we can turn these carboxylic acids into acyl halides, right? If you want to turn into a bromide, use PBr3. By the way, I'll talk a little bit about mechanisms during the mechanism portion about how to make them easier and, which ones I think are, good for no card and which ones aren't. So this is right now just sort of like a reaction starburst, if you will, just like what reactions are possible, what you should know. Okay, cool. So SOCl2, right, turns into acyl halide. Remember, the HCl reaction doesn't really accomplish that because mechanistically, when we get to that tetrahedral, right, always the group that's booted off is the Cl. But if we were to heat this up in the presence of HCl, we can get a dimerization into the anhydride. Okay, so we can make symmetric anhydrides. But here it's a dimer essentially. Okay. If I take that acid and then I add in a nucleophile that's better than the carboxylic acid, as in an alcohol, then I get the Fischer esterification process. Okay, so it can make esters. Okay. So for the most part, you kind of just throw in a nucleophile and it substitutes out the OH group, right? That's the big part in these reactions. But when you add in amines and really, any type of molecule that's considered a base in the face of a carboxylic acid, right? Predominantly the reaction that we get is going to be the acid-base reaction. So look at this here. So we'll get the carboxylate. Okay. And the number one thing about the carboxylate is it's super, super stable. So once you form a carboxylate, not very many things can punch through this. So one of the best explanation questions you can get is, why does carboxylic acid and alkoxide not form an ester? It's because the alkoxide forms the carboxylate, super stable, and this is unable to break through that. Okay, so unfortunately that reaction doesn't work very well. Okay, so what's considered a base, right? What things can go through this for the most part, right? You can think any type of amine, right? We'll go through this. Any type of, again, alkoxide will go through this. A hydride will do this, right? Organometallic will do this. It just turns out that really the only thing that can punch through this is anything that's as strong as a lithium aluminum hydride. That will completely reduce this down, right? So this and then water, right, will give us the primary alcohol. I'm not sure if you really talked about this, but let's say you have an excess of organometallic or you have Grignard. It doesn't matter which one. I just chose to write the lithium reagent here, but you can get the ketone. Okay, but I'll put a star here. I don't think you guys really talked about that. Cool. But if we're thinking about, alkoxides and, amines, usually, these guys stick around here at the carboxylate. Eventually, though, right, for the amine, you can get some reversal. And if you do heat it up, you can get a reaction. But this reaction is much more industrial, right? You kind of just put a ammonia and acetic acid to a pot and you kind of just boil it for like days, weeks, months, years, right? So I personally would not recommend you guys try to use this, but I know that a lot of you are always a bit of, oh, we saw it in class, so it should work. It works on paper. And I guess that is true, right? Technically, it does work on paper. So I guess you could get away with it, but just generally speaking, carboxylates, very hard to attack as electrophiles. So basic nucleophiles or whatever counts as a base in front of a carboxylic acid, it's not the best choice there. Okay, cool. Now, aside from that, all we really have left is the HVZ reaction, which has different ways of being written. The way that I write it on the exam a lot, and I've seen it written, is trace PBr2, right? Point of that is to ensure that there is a low concentration of PBr3, because imagine if there was a full equivalent, right? You just get the acyl bromide reaction. But if you have less than an equivalent, if you have less than equivalent, you have a low concentration, you do allow the HVZ pathway to take control, and we end up with the carboxylic acid that is alpha brominated. So let's just take a second to talk about these alpha brominated species. And I'll add this little tail here so we can kind of track things. But what makes these very interesting is that back in 118B, you guys talked about, right, how, well, bromides are great electrophiles, but if we put a pi bond next to them, they become even better, right? Allylic bromides. And so this is like allylic on steroids, right? Because you got a carboxylic acid species there too. So you can imagine SN2 reactions are a lot better, right? Although, I mean, funny enough, I mean, again, this amine will salt with the carboxylic acid first, and then eventually it will undo the salts and will add to that, it will substitute out that bromine. But we can potentially make alpha amino acids, right? Which hopefully you guys knows what these are. If you don't, right? I mean, consider what is helping me talk right now, or helping you write, or helping you look, right? It is the oligomerization of amino acids, right, into polypeptides that allow us to even talk and do any of our daily functions. So if you ever see an amino acid, say in synthesis, or you see the sequence of HVZ into ammonia, right? That's a HVZ type. That's a HVZ type reaction. Okay. We can also add in, let's say, cyanide, right? Cyanide's a good nucleophile, and I mention it because, hey, look at that. I have a CN here. And we know what CNs do when you hydrolyze them, don't we? They turn into carboxylic acids, right? So look at that. We can make these interesting carboxylic acids, these alpha diacids, which actually is kind of funny. This is actually super hard to isolate. You'll learn why in chapter 23, I think, but these are actually super hard to isolate. So maybe you won't show up, but it's a cool thing to recognize and notice, right? I mean, consider what else you could do with the CN. Right, there's so many things you can do. I just don't, I don't want to spend too much time talking about all of them. Okay, cool. Last one I think is worth noting is OH minus, because that's also a nucleophile, and that makes these alpha hydroxy acids. And you can imagine, I mean, what can you really do with that, right? Maybe just PCC it or something, turn it into an alpha keto acid. So if you ever have an alpha substituted species, right? So an alpha substituted acid, right? Consider that it came from the HBZ alpha bromide. Right, so a very good synthesis cue right there. Cool. Again, this is supposed to be sort of more of a surface level review, so I won't get too much into it. I don't want to waste too much of you guys' time. Cool, but that's the carboxylic acid. Some notable examples here to just keep keep track of, or be mindful of. Right, remember that dioic acids. Right, so if I have two carboxylic acids together on a chain, I can heat them up, or I can add SOCl2 to make a cyclic anhydride. Right, so that is a possibility. If it's an alkene, right, you want to make sure the alkene is cis so that they're on the same face of each other. But anyways, right, dioic acids can intramolecularly attack each other, or attack themselves. Keep in mind that the SOCl2 reaction works by first acylating one alcohol, right, or one carboxylic acid, and the other one is enticed to attack. Right. I know somebody would be like, oh, shouldn't you attack from here? And yeah, I could, but I mean, I passed the class, right? So I can do whatever I want. You guys still got to do that. So damn, stuttered. They didn't hit us hard. Anyways, cool. And then if we keep that same idea that we can do these intramoleculars, you can imagine anytime you have these alcohol tails, right? If you want to cyclize on them, you totally can. Again, this will just take H+, or you can use SOCl2 pyridine here. Right, whatever you need to activate the center here. Okay, cool. All right, so that's the carboxylic acid reactions, and we'll see a couple of those, right? That's all of 19. 20 is going to be all the derivative reactions. So if you want, I mean, to be honest, when I was thinking of this and making the exams, I pulled up your guys' study sheet, and I mainly did, I mainly worked on this exams using that. So that'd be a good thing to look at, especially that table. But we'll start with the acyl halide, the first of the derivatives. One thing to understand with the acyl halide is the most reactive derivative. This thing will react with the moisture in the air. So in lab, when you prepare these, it's usually air-free, covered, you reacted same day, probably in the same hour, same 30 minutes that you made it. It reacted instantly. You don't save this thing. It's not bench stable, because even with the moisture in the air, this thing will react. Okay, so if we hydrolyze it, we get a carboxylic acid. You can choose to use the conjugate bases of all the nucleophiles we talk about. That's totally fine. It's just a stronger reaction. And you don't necessarily need to do it, right? Water will just hydrolyze this. Right, we can react this with organic water or alcohols, and what we get out are esters. Usually, because of the HCl byproduct, which could kill you, right? Make you dead. We add in a little pyridine. So I've actually done this reaction. It works really fast. You could use you could use the conjugate base here. So you could use O-, but it's kind of an overkill if you ask me. As long as you have the pyridine in there, it tends to work out pretty well. So we can make esters pretty well, right? Hey, guess what? If I have another carboxylic acid, right, different from the carboxylic acid that made my acyl halide, right, what I get is an asymmetric anhydride. Okay, so remember earlier I mentioned that to make symmetric anhydrides, you would dimerize an acid by, throwing in some HCl. In this case, right, if I wanted to make it asymmetric, right, I'd go through the acyl halide. Now, because there is no proton on that chloride, that is, annoying. If I use an amine, and again, I don't even really have to heat it, I can just use an excess of it. I will get out my amide, and with little consequence or little, worry about, oh, is it going to, react with a proton, get stuck? It's not going to take long at all, right? So the acyl halide, it's kind of like the carboxylic acid in that it can make everything other than itself, right? But it does everything better. So synthetically, if you ever feel the need, you're like, oh, I'm not sure if the carboxylic acid would do it, just turn to an acyl halide. That's how people do it in lab too. You would start with the acid. If the acid reaction doesn't work, then you try the acyl halide reaction. And more times than not, it ends up working. So it's very reliable. Okay. So synthetically, right, if you think you need to acylate something, whether a nucleophile or add an acyl group in what way, acyl halide is your job, right? That's your thing to do that. It makes all of these derivatives here, right? So what happens when we reduce them, right? Well, if I use something like a lithium aluminum hydride, right, or NaBH4, either one of these hydrides, right, initially we'll get the aldehyde, but again, aldehyde's also reduced by these reducing agents, so we end up getting the primary alcohol. Okay, we'll be seeing this problem all throughout, so recognize this, right? With most derivatives, this is the exact same issue we have. Okay, so how can I stop this? Well, if the issue is that we have an overreaction because aldehydes also react, let's just get rid of all the hydrogens, right? So if I use lithium aluminum OR3H, right, where I limit it to one hydrogen and I do this one equivalent, right, I can stop at the aldehyde, right? When the molecule here, right, this H minus, when it has to decide whether it attacks an aldehyde or an acyl halide, right, just consider who's more electrophilic, right? Both of these have a methyl, so there's no difference there, but the hydrogen has no effect on the carbonyl. The chlorine has a withdrawing effect. So always acyl halide is more electrophilic, and more times than not, this here we call LITBA, or that's like sort of the easy way to name this, LITBA, right? LITBA will attack the acyl halide over the aldehyde. Cool. So you can imagine then with Grignards or with organometallics, right, we have the same issue. Let's put RM here, right, where we go through a ketone, but we get an overreaction, right, if we have an excess of this, and usually will be dealing with excess of organometallics, right? Right, we end up getting the tertiary alcohol. Okay, tertiary symmetric alcohol, I should put, because you're adding two of the same group, so it's symmetric now. Okay. Really important, that symmetry aspect, by the way. So how can we stop this? Well, it turns out acyl halide does have a solution. You just use something that only reacts with halides and not with ketones, and that's the Gilman reagent. Okay, the Gilman reagent. Yeah, so I'm going to put a thing here, right? This is actually a really important pathway because in this class, there's only really two ways to make ketones, right? Aside from this one over here, we'll ignore this for now because I'm not sure if you guys covered that. But acyl halides provide one pathway to the ketone. So if in synthesis you recognize you need to use a ketone, acyl halide can be one of two things you can use. The other thing we can use is a nitrile, as we'll see. Okay, cool. So acyl halide, again, this has the most reactions. And for good reason, right? It's so reactive, it'll just react with anything. It'll acylate any nucleophile. So with the anhydride, we call the acyl halide and the anhydride acylating agents. And this just means that if there is any sort of nucleophile in solution and you introduce the halide, the acyl halide will just give up its acyl group to that nucleophile, right? So a majority of reactions with these guys is just, hey, give the nucleophile the acyl group, right? Actually, one reaction that we don't really talk about anymore, despite the fact that we talked about it a lot in 118B, I don't have a lot of space here, so I'll kind of snake it in here, is let's say that my nucleophile is a benzene ring and I add in Lewis acid to make this reaction go faster, right? This reaction was essentially acylating a benzene. And for good reason, right? Why we use acyl halide there in anhydride. Those guys are the most reactive. Okay, cool. So I wouldn't worry too much about this one, but it's a good reminder, right? Like we've seen this before. You can even imagine, right? Remember, if we had a phenol, right? Where did that acyl group go? Went on the oxygen. Okay, just acylated the oxygen. Okay, cool. So just things to keep in mind. Just reminding you guys of these reactions. Okay. Now, the nice thing here is that the acyl halide and the anhydride essentially do the same reactions. So all these reactions that I've described here, right, anhydride can do as well. I know some of these were not checked marked on your table, which is fine. Don't stress about that. If it's not checked marked, it means that he's not going to hold you responsible for it, right? You don't need to know the reaction or the mechanism. It's because he's not sure or it doesn't work or, something of the sort, right? So don't stress about it, right? But anhydride can do everything an acyl halide can, right? Anhydrides they're thought of as safer acyl halides. That's why you guys use acetic anhydride and you guys don't make acyl halides in lab. Because again, that HCl component is it's a little scary. Yeah. Cool. So look at that. With just one chart, we're able to describe two sets of reactions, which is great. So when we move on to the ester, right? How is the ester in comparison to acyl halide and the anhydride? Well, in the anhydride and in the acyl halide, especially acyl halide, right? The lone pairs on that X group, on the acyl group, don't really contribute too much, right? We'll talk about this later with the general knowledge questions and the trends. But acyl halides don't really, they don't really resonate, right? If anything, they're more withdrawing than they are resonating. Right? They're inductively withdrawing. So these guys are typically very reactive for that reason. Same thing with the acetyl group too. But the ester oxygen here is very capable of donating, at least relatively speaking, compared to the anhydride and the acyl halides, definitely more significant. And so because of that, it's a bit more resilient, it's more stable, right? So esters, the number of reactions significantly drops in that, we can only really make carboxylic acids through hydrolysis, right? And again, whether you do H plus or OH minus will dictate which one you get. And I'll put here OH minus, right? You can make other esters. So you can choose to do this in acid, or you can choose to do this in base. It won't matter, right? So we can do what we call a transesterification. Or we can make amides, right? So if you just have an amine and you just kind of heat this up, right? Eventually this will push forward towards the amide. And again, depending on the type of amide or amine you use, right? You can get a different type of amide. Okay, cool. But that's about it, right? You can't make anhydrides, you can't make acyl halides, right? Because if you think about the tetrahedral, right, you're essentially asking a tetrahedral to give up an O minus over an acetate, which is probably never going to happen. And especially you're asking an O minus to give up you're asking them to give up an alkoxide over a halide. That's never going to happen. Okay, so thinking about this, these can be really great explanation questions, right? Why is it that an ester can't make an acyl halide or make an anhydride? And it's because you're asking for a group that's not very acidic to fall off and a group that is acidic to stay on. And that's not really how that works, right? Our general rule of thumb is you want your nucleophile to be a better a better base, right? You want your nucleophile to be more basic than your leaving group. That way, this is promoted in leaving. Okay, cool. All right. Now, when we think about reductions, again, if I use something like lithium aluminum hydride, so that super punch, right, we'll go through the aldehyde first, but this gets reduced pretty quickly into the alcohol. NaBH4 will not work here, by the way. NaBH4 is not strong enough. Lithium aluminum hydride is the only thing that's strong enough to do this. So this could be a very good chemoselectivity question, right? You could be asked, okay, I have an acyl anhydride and I have an ester, right? Who reacts with NaBH4, right? Definitely going to be this guy. Or actually, I think on your chart it only said halide, so we'll go with the halide, right? So definitely it's the acyl halide and not the ester that's going to react here, right? This would not react, this would. Right. But if I had lithium aluminum hydride, both do react because lithium hydride punches through anything, right? In the lab, that's kind of seen as like the almighty reducer. It will reduce things you don't even expect it to reduce, like alkyl halides, actually. So how can I prevent this? How can I stop this? Well, you might be thinking, okay, maybe I use LIPA, and LIPA could work here. LIPA is, a nucleophilic reducing agent, right? It's the H- that can attack. But remember that these derivatives are a lot more resilient, and you don't really want to punch too hard, especially you don't want to use a super reducing agent in presence of others. So usually the typical plan here is to use something like Dibble. Okay, so Dibble, I won't get into the details of it too much because you guys didn't cover it too much either. But Dibble is actually an acid. It's a Lewis acid, so it's alane here, right? It has 3 bonds, so it's a sextet. It's looking for electron-rich carbonyls. Right. Once it complexes, so we'll have like the R2 group here, have a H here, right? Aluminum with a minus is when we activate the hydride, right? That's what I mean. If you think about LIPA, right? LIPA is aluminum minus because it has 3 R groups on it and a hydrogen, right? Well, this is the same thing. Once the Dibble adds onto the carbonyl, we have aluminum minus, right, with 3 things on it and the hydride. So this is when the hydride can attack. So Dibble highly relies on electron richness to be activated and reduced. And so it makes it so that it's actually very chemoselective. So remember that question I just asked a second ago where I said, hey, let's say I had an acyl halide and an ester, right? And let's say that I did Dibble. Guess who, if I do one equivalent of Dibble, guess who Dibble reduces, right? It reduces the electron-rich carbonyl, right? So it's only this guy that gets reduced into the aldehyde, right? This guy doesn't get touched at all, especially at one equivalent, okay? And at that low temperature, okay? Now, mechanistically, I would say just write down the net mechanism guys saw in class. I don't particularly totally agree with it, but that's totally fine, right? What's important to understand is what I just said, right? Is how Dibble works. But anyways, save a little bit of time here. So we can use Dibble here. Not that LIPA won't work. It will. It's just, I mean, it's a super puncher, right? So if you have any other groups on your molecule, it's also going to hit those things on top of the ester because the ester is resilient, right? So what happens if I use an organometallic? Same exact issue, right? Like I said, we're gonna see this for at least for this one. We're gonna see this for all of the derivatives, right? Grignards are so basic. They will pretty much substitute anything, anything you can imagine. So we'll get the tertiary symmetric alcohol here. Okay. All right. So the number of reactions with ester has dimmed down a bit, right? And essentially, it's you either turn it into a carboxylic acid, you turn it into another ester or an amide, and then you can do your reductions, right? There is no ketone solution here, by the way. There's no arrow that does this. So again, that's why it's important to recognize, if you recognize a ketone, you've essentially boiled down the number of reactions that you can do, right? It's either acyl halide or, as we'll see, the anhydride. Okay, cool. So these are the ester reactions. Aside from that, we have the amide, which I'll first talk about the tertiary amide, and then we'll talk about the primary amide. But amides, I mean, they are, if ester is resilient, then amide is, powerful. It is the rook, right? It is a stone wall. And unless you are leaving this overnight, boiling, spinning 24 hours, right? Nothing is really going to happen. And some of you might actually have experience with this. If any of you work in like a biolab and you've had to ever use like an autoclave or anything to like destroy a protein overnight, what you're really doing is breaking amides, right? Because that's what proteins are. Polypeptides. You guys remember this from CC. Okay, yeah, I did that right. Okay, there we go. Right. Polypeptides are just amides, right? It's this bond here. That's what you're breaking in polypeptides or in proteins. Okay, so cool little thing there. Okay, so it's a good thing they're resilient, right? Because if they weren't, then we would just be puddles of water, right? That's not very fun. But aside from that, right, what else can we do, right? We can only really turn it into carboxylic acid carboxylate, can't really turn into other amides, can't really turn into esters or anything. So all we have left are just reductions. So again, if I use lithium aluminum hydride here, right? A lot of you might be tempted to just do this, which, you know, even I am tempted sometimes to do that as well. Because, you know, you're like, hey, that oxygen there, right? Or that alcohol there, that's what we've seen this whole time. But the cool thing about the amide is that, or I guess the not so cool thing is that on the amide, the nitrogen is such a bad leaving group that it actually forces most of the time the oxygen to leave, which is kind of interesting. So in the case of lithium hydride, actually, instead of going through the alcohol, we actually, or the aldehyde, we go through the aminium. And it's the aminium that's getting reduced. So we end up getting amines. So if you ever find yourself making an amine, right, especially where you think a carbonyl might have been, lithium hydride is your way to go there. So this is a nice little thing to look for. Okay. On the other hand, right, if I use Dibble still does work here. Again, I mean, this is the most electron-rich center. So you can imagine with amides, this reaction is the fastest. But we can make aldehydes with the amide here. If I use a Grignard, a couple of you might be thinking, oh, okay, so if we take the idea you just said earlier, using like a Grignard or using an organometallic, that should shred this into some kind of amine. But I mean, organometallics are so basic. I mean, they're much more basic than a hydride and much more basic than an amine. They'll force any group off. Usually what you'll get is a tertiary alcohol. Right, this is the pitfall of using any kind of organometallic, right? You get a tertiary symmetric alcohol. So actually, one of the solutions that I thought you guys were going to learn is actually through the amide, right? And the reason for that is if I use a particular type of amide, I'll only rant for a little bit. So if you use something like this amide here, this is called a Weinreb amide. What ends up happening is that if you do the Grignard addition, and you guys kind of saw this with the Dibble mechanism too, but it turns out if I have an amide that has some kind of like atom on it with a lone pair, the lone pairs on that atom and the carbonyl oxygen can actually complex with or what we call chelate. They can chelate the magnesium so they can hold the metal in place. And you can see this makes like a 5-membered ring, and that actually stabilizes this intermediate. So much so that you can get it through hydrolysis and get out ketones actually. So we can do hydrolysis now and get to a ketone. So amides do offer the most industrially sound, viable pathway to making ketones, and yet we don't talk about it. Just kind of interesting. So anyways, there's other ways of doing this, right? As long as there's some kind of, again, chelating agent. So, I mean, this could even be like 2 atoms down, right? Because this will just make like a 6-member transition. Actually, for any of you that are interested in organic, I'm not sure how many of you guys are, but if any of you guys are, the class 231, which you have to take after 131, goes into things like this, like goes into depth of how the 3D conformation of the 6-membered. I mean, you can imagine if this is a 6-membered ring, a cyclohexane essentially, it goes through a chair. You'll study those kind of things. So if any of you are interested, let me know and I can tell you more about that. But anyways, yeah. So yeah, so there is a sound way of making ketones out of amides, but again, it requires that chelating atom on the nitrogen, which we're assuming there isn't. So we always go to the alcohol because that intermediate just collapses. Okay. Again, there is no solution here. It just always goes to tertiary symmetric alcohol. Okay. So again, this here is a very nice synthetic cue for like, hey, just take a acyl halide or anhydride or ester or amide and just kind of throw some Grignard at it, right? And it just tends to work. Cool. So this is the tertiary amide. So the amide that's not very, useful, or not that it's not very useful. It is useful. It's just a little boring, right? That it doesn't do very many reactions. But when we talk about the primary amide, things get a little interesting because, like the carboxylic acid, the primary amide does have these protons here, right? So it has these sort of carboxylate protons, or we call it amidate protons. The pKa of these guys usually around 17-ish, 15, 16, 17, around there. So a little more basic than a hydroxide. So if I use like a hydroxide, it'll mainly be on the left side here, not the right side, sorry. But you can pull it off, right? Because you just need something within the range. But this amidate ion is really interesting. You can do a lot with it. Namely, you can, if you think about this as an enolate, right? If you consider this like an enolate, you can do an alkylation with a primary or a methyl. right? And so we can get what we have here is an amidate alkylation, right? If we use Br2H2O, so bromide water, what we get is the famous Hofmann rearrangement. Okay, and so if I kind of put like a handle here so we can kind of track what happened, a lot of people like to think of this reaction as a, removal of a carbon or removal of the carbonyl, and that's totally fine. I offer a different viewpoint. I think it's better to think of this as you're replacing the entire amide function with an amine. And the reason why I like to think about it this way is because remember, amides, they can be made by everything. If you go back and look at all the reactions we talked about, everything can make an amide. So really, to think about the Hofmann pathway, or if you identify a Hofmann pathway, you always know how to make it, because everything in the world can react with ammonia to make the primary amide, and then the primary amide can then just be reduced down in the Hofmann rearrangement. Okay, cool. Well, it's probably, I think the mechanism question was on this. We'll talk about it. I don't remember which one it was for this example. We'll see. Cool. All right. So other than that, what else can the amidate do? Not much else, not that anything I can think of. But yeah, it's primary amide. Nothing really changes, right? If I do lithium aluminum hydride, right, same reaction. Again, yes, it will go through the amidate, right? But I mean, lithium hydride, there's 4 of them, so it'll just absolutely devastate. It'll destroy that carbonyl, right? If I use one equivalent of Grignard, right? Just like with carboxylic acid, if I use one equivalent, right, yeah, I'll get to here, but if I use an excess, it'll just, again, shred it to pieces, make that tertiary symmetric alcohol, right? Stuff like that. So, things to consider. Dibble, I think you would have to use 2 equivalents of Dibble here. I think that's the protocol for this. Yeah. You would definitely have to use 2 equivalents, because the first equivalent of Dibble will quench on the, so when we get to here, right, the first equivalent will quench there, which will make it an amidate, which is much more electron rich, so that the second equivalent of Dibble will add an attack. So yeah. Cool. All right. So that is the primary amide. The last reaction I'll show you that you don't need to know, but it helps to segue really nicely into the last derivative here, is if you take a primary amide and you dehydrate it with SOCl2, you make a nitrile. Yeah, that's a fun mechanism to try if you want to. And so nitriles are our last derivative, and they are just as resilient as amides. In fact, they are, they're dehydrated amides. So the first step in this reaction, these hydrolysis reactions, is, hydrating it back into the amide. And so that's why these are usually they feel very long, but in fact, they are just, pushing towards the amide and then doing the amide hydrolysis reaction. Okay. But these guys are so resilient. I mean, acetonitrile is a very popular solvent just for that reason. Takes a lot to motivate these guys to react, but other than that, you can only really do reductions. Dibble gives you the aldehyde. So, associate Dibble with aldehydes, right? That's like its one job, to make aldehydes. Interestingly enough, right, like I mentioned before, if we use Grignard, even if in an excess, right, what we go through is the imidate ion, which upon hydrolysis hydrolyzes into a ketone. So remember how I mentioned that technically there's only 2 pathways to make ketones in this class, right? These are the 2 pathways. You either do it through nitrile with the organometallic, or you do it a Gilman with an acyl halide. So you've only offered 2 pathways of doing this. So synthetically, this can be a very nice cue on what to do. Okay, cool. The reason why excess doesn't mess with this is because this imidate is actually very stable. It absolutely does not want to react with the organometallic once it's formed. So it's already very electron rich. Cool. But with that, right, those are the reactions. Those should be the reactions. Should be sufficient for predictive products at least. Big thing that I think people struggle with, sort of takeaway here is, there's so many of these reactions, but as we'll see, a lot of these are the same. I mean, if you really want to break it down, carboxylic acids, for the most part, make other derivatives. That's their whole deal. They make other derivatives. And then, reductions. And then, I mean, the reductions are pretty much the same for all of them. But anyways, we get reductions and the HVZ reaction, right? Acyl halides, for the most part, kind of just make every single derivative. So if you want to throw an acyl group at something, you use the acyl halide or an anhydride. That's kind of those guys' job. They do absolutely the most amount of reactions and react with practically everything. Esters and amides are much more resilient. They can only really make each other, and we do usually use them for reduction sequences. And then nitriles are solely reduction sequence, right? There's a couple oddballs in there, right? Like, there's the Hoffman, there's the HPZ, there's the yeah, that's about it. Those are like the three, in my opinion, like oddball type reactions. But those are not too bad. Not hard to remember. I mean, you have a node card for a reason, right? So using that node card as a second brain can really help out with some of these that don't really match up. Okay. Again, mechanistically, we'll talk about mechanisms when we get to the mechanism unit, and I'll give you guys a couple tips on how to memorize most of them, or not really memorize, but if you understand like 2 or 3 mechanisms, you memorize all of them really. Okay, cool. I think the only thing that I might have forgot to talk about, just cyclic stuff. So just keep in mind that cyclic reactions can work, and actually it's fine because I know there's a couple cyclic types of reactions in the document. Cool. So with that being said, let's just get into it. Hopefully you guys took a pass at this. Because I'm assuming you are, I'm just going to go ahead and just straight up just do this. I'm not going to try not to waste too much time here. Cool. So with A, we have a carboxylic acid, SOCl2, first step. That's super iconic. That's going to be a chloride. Okay, that's going to be a chloride there. And again, remember, chloride just throws its acyl halide at anything, or its acyl group at anything. So we have an alcohol in the second step, and I guess I should have put pyridine here, but technically it's already in this step, so it's okay. But all that's going to do is acylate, right? That's its one job, is to acylate that alcohol. Okay, so there we go. We made an ester. Okay. Now, one thing that I do want to say before I move on to the other problems is I know that a lot of you guys were worried about not having practice. I mean, that's really the reason why I made these 3 midterms, right? So that you guys have ample amount of practice. I have absolutely no idea what the format's going to be. I just kind of asked someone for the midterms from last quarter, the 2 midterms from last quarter. I kind of just looked at the format and just kind of, was inspired by it. But what do you do when you only have limited practice and you want to maximize every problem, right? Like, what if tomorrow I get hit by a plane and then I'm out of commission for the rest of my life, right? I broke my hands. I can't draw anymore. I can't make this anymore. What do you guys do, right? If AATC suddenly burns down, right? Because someone was not happy with their performance in the class and decided to take it on them. Well, what you do is you take problems that you have and you add extra stuff to them, or you take different routes with them. For example, who in the world said that the first step had to be SOCl2 and then the second step had to be an alcohol, right? I mean, maybe I keep the first step the same, but what if the second step I use an amine? Like, let's say I used this amine here, morpholin, right? Ask yourself the question, how would this change the reaction, right? What would it look like in practice drawing that, right? Well, if all that differs is that I just attack the nucleophile with the acyl halide, right? That just means that I'm going to make this instead. Right. So you guys actually have, 30, I mean, you have 10 questions on the page, but if you do 3 types of reactions for each, you actually have 30 problems you can practice. Right. I mean, what if I instead decide to do Dibble here, or not Dibble, let's say LIPA, because that is technically what you would want to use for the acyl halide. So the lithium aluminum R3H, right? What if I did that? Well, that just means that I'm turning that acyl halide, right, into an aldehyde. So I just put an H here. And look at that. Now I've been able to practice 3 reactions. So we'll do this for the rest of them, right? We'll do 2 more reactions on top of what we have written on the page. And you'll see quickly, every single exam really is a gold mine of 100 questions. I mean, in this case, it'll be 30, right? Because there's 10 questions and we're just doing 2 extra variants, I think. Yeah, so we'll have 30 total questions. But it can be up to like 50 if you just do different nucleophiles, right? I mean, really the choice is yours. Like, what if for the first step, I actually did, well, I guess the first step wouldn't really change anything, right? Like this is always gonna make a derivative. The second step that really matters to change, right? So, changing out that step. So we just did 2 of these, and, on the physical key that I write, I'll try to, I'll probably make an extra section where I do these extra ones. So don't worry if you think that you're missing out if you don't watch these. I'll just throw on the extra ones I did. So there's 2 that I just did for this one. I'll throw them on at the end. Yeah, cool. All right. Lithium hydride. Remember, that's super punchier, right? And like I said, I didn't really talk about cyclics, but that's great. It's okay because there's cyclics in these, so we can talk about them, right? Generally speaking, right, when it comes to cyclics, people are a little bit afraid of them, but don't be, especially with anhydrides. Usually if there's symmetric anhydrides, you just kind of choose one side and you just cut the derivative bond. So we'll just cut right here. And you can kind of just copy everything out. So for most part, it'll look like this. And then just consider what the nucleophile is, right? And you can just add it there. So if this were like water, or like, let's say it were just water, then, so if this was just water, then it would just be like an OH kind of situation. So you make a dioic acid. If it were like an alcohol, right, you would make an ester acid, right? In this case, though, what we have is lithium hydride, which again goes through the aldehyde, but then also punches through the aldehyde, right? It destroys it into an alcohol. So we get the primer alcohol here. And so this here would be your 3 out of 5 answer. Why would it be 3 out of 5? Because remember, lithium hydride, I guess I should have put excess here, but it doesn't really matter because you need, yeah, I guess I should have put excess here. So I should have made that clear. But anyways, you can also reduce decarboxylic acid too with lithium hydride. That will also reduce. So you'll get both reductions here. Notice that cool little thing I did there, right? With the carboxylic acid, all you're really doing is erasing the carbonyl. So that's a nice way to recognize it. It's a nice way to apply it. But we get a complete reduction of the system. Okay. So how can we change this, right? One thing we did was we said, okay, let's just change it to a different nucleophile. So let's say that we just did an alcohol here, right? Alcohol, again, would just give you ester on one of those ends. And I'm choosing the top. You could have chose the bottom. That's totally fine, right? That would have just gave me that, right? What is something that would give me the 3 out of 5 answer as the full answer, right? What if I used NaBH4, right? We talked about this. NaBH4 only really works on anhydrides and acyl halides. Everything else just kind of throws it away. And that's what we see here, right? We see that NaBH4 would only do a partial reduction, right? Because it can't reduce carboxylates. Okay. So look at that. We were able to do so many more reactions if we just think about other nucleophiles and also see the substrate scope, right? What are acceptable answers that we can draw, right? Cool. All right. Hey, look at that. Primary amide, and we have a Hoffman rearrangement, right? We have Br2OH minus, a very common setup. So again, for me, the easy way for me to think about this is I'm replacing all of this with NH2, right? For some of you, it might be easier to think about getting rid of the carbonyl, do whatever you got to do. Just thing to know here is that stereochemistry is retained. No loss, right? It's retained. So that's where stereochemistry can come in, okay? One of the 2 ways I can think of that will come in. Yeah. So what are other things that I could have done here? Maybe instead of Br2 and H2O, maybe I did this bromide, right? How would this change this? I mean, in this case, you would go through the amidate and you would just do an alkylation, right? So we would just be adding this here. Okay. What if I did Dibble, right? Or you know what? Let's say I did lithium aluminum hydride, right? What would that do? Well, remember, that doesn't give me the alcohol, although I want to draw it. That just kind of erases the carbonyl. So amides and carboxylic acids are kind of the same in that you just kind of erase the carbonyl and it's a lithium aluminum hydride reduction, right? What would Dibble do? Dibble would just turn this into an aldehyde, right? So let's say that I have this here, right? This would be the Dibble answer. Okay, cool. All right, hope you guys are seeing how much more practice we can do, right? Having a lot of fun with this. Cool. All right, so again, this is my way of writing the HVZ. I'm not sure how you guys will see it. Hopefully there'll be practice problems where you can see, but for me, this is a clear indicator of HVZ. So I can go ahead and do that. And remember, HVZ makes this powerful electrophile that the second step can substitute. So sulfur CH3, right? That's just going to substitute that bromide there. Okay, it's a very common sequence that you will see on these exams. Cool. So how could this have changed? I guess really the only thing that changes is what you put here. So let's say we put CN minus, I would just put this here. Let's say that we put, what else can we put here? Let's say that we put, or not S3, sorry. Let's say, I guess OH minus or ammonia, right? I'm not sure if you guys recognize this. If you guys know what amino acids is, it's actually alanine. So I know, some of you guys might be bio inclined, so it makes it kind of fun to know that. Cool. All right, we got a multi-step here. A lot of steps. Looks like we are starting with the bromide. We'll talk about this more when it comes to synthesis, but because I didn't really want to talk about this earlier. But when we start from bromides, that's how we make carboxylic acids usually, or that's usually a cue that we want to do that. Not necessarily the case here, but usually when it comes to bromides, we can either take an Mg pathway or a CN pathway. We'll see how those differ when we talk about synthesis. Okay, cool. But in this case, we have CN minus doing an SN2 type attack. So remember SN2s, those are backside attacks. So get this here. And then again, there's a couple different ways we could have resolved this, right? If I take the hydrolysis pathway, which is usual pathway here, this turns into a carboxylic acid or carboxylate if I did it in base. I chose to use a Grignard here. So I'm going to, remember, nitriles and Grignards give us ketones. So a way to easily predict this is you replace CN with a carbonyl, and then whatever your Grignard is, right, that's what you're adding to the other side of that ketone. Okay, cool. So that's our access to asymmetric ketones. And again, that stereochemistry component, right? That really matters there. Okay, cool. All right. So that's, I mean, that's how this really changes, really. I guess you could have done Dibble instead. So we could have done this and gotten that. That's totally possible too. Cool. All right. Okay, so F, I imagine, is going to trick a lot of you guys, which is okay. That's the reason why I wrote it. It was to be a bit tricky, so it wasn't the easiest thing in the world. But if we kind of walk through the sequence here, right? Remember, Cn minus can substitute something like a bromide. Alcohol is untouched. And then we do a hydrolysis. So obviously in hydrolysis, you replace this with a carboxylic acid. Okay. But a lot of you might have seen this and thought, okay, OH and carboxylic acid, right? This looks like the beginnings of a cyclization. Right. And so a lot of you might be thinking, okay, what you wanted was for me to realize that and to do this. Okay. And yeah, if you did this, I'm happy that you did because I wanted you guys to fall for this. The reason why this is not the answer is because we're in hydrolysis conditions, right? And specifically, we're in nitrile hydrolysis conditions, right? I mentioned that when it comes to nitriles and amides, those guys are super resilient. The hydrolysis conditions for those are the harshest of them all. So in the event that, yeah, you do get the ester, right? I mean, esters are more reactive than amides and definitely more reactive than nitriles. So if you're hydrolyzing a nitrile and you make an ester, right, then the ester is also just going to hydrolyze. This is actually just going to reverse because the condition is just that rigorous. So the trick here was to give you something that you wanted to use and knowing not to use it. So I apologize. That was a bit of a mean one, but it is something to think about, right? If you make the ester from a nitrile, consider that maybe you're just, you're in a condition that's a bit more harsher than that. Yeah. The other exams don't have tricks like that, I don't think. Like if there is a cyclization that I want you to cyclize, it will cyclize. So cool. But I guess let's actually let's actually consider how would it look for this to be the hydrolysis? You'd then have to have an H+ step afterwards and heat, right? So you'd want a hydrolysis condition and then you'd want a cyclizing condition. In this case, yes, now we do want the cyclization. So we would want is it 5? 1, 2, 3, 4, 5, 6. Oh, it's 6. Sorry. Right. 1. Oh, maybe just. So I like to do is 1 attacks, 2, 3, 4, 5. Yeah, it is 5. Never mind. It is 5. Right. In this case, yes, you do want the cyclization. If you have that third step where you're forcing that dehydration out. Okay. Cool. All right. So what are ways that we could have changed this? I guess instead of doing like a nitrile hydrolysis, I guess you could have done like a Grignard or something. Right. So CN. And then add in like MgBr. In this case, right, that'll give us the ketone. Right, 1, 2, 3, 1, 2, 3, yeah. Okay. One thing you guys not remember is that if you ever have a hydroxy ketone or hydroxyaldehyde, these guys actually are in equilibrium. They're usually in their cyclized hemiacetal form. So in this case, it is much more likely that this actually looks like this. I don't think you need to know this though, but it is something worth writing down, I think. Just so you guys remember that. Cool. All right. Moving on to G, we have an excess of amine and we have an acyl halide. Remember, acyl halides will just acylate whatever nucleophile you have, and our nucleophile here is the amine. So we're just going to go ahead and acylate it, right? Add that acyl group, right? And then from here, it looks like we're doing NaOH, which makes the amidate, and then we're adding, looks like an ethyl. So we're doing an amide alkylation here. So nothing too crazy. Ways this could have changed is maybe instead I do lithium aluminum hydride, that second step. Right. And what that gives me is this here. So this amine here, right? We just erase the carbonyl. That's totally possible. Maybe instead of using the acyl halide, I mean, this could have been anything, right? As long as it's an ester anhydride or an acyl halide. Oh, actually, I guess I didn't really address this, so we can talk about this now. So if it were a symmetric anhydride, you don't really have to care about where it goes. If it were asymmetric for whatever reason, usually the bulky side is the one that we avoid. So we would attack here, right? We would very rarely attack on the bulkier side. So that's something you might want to consider. I don't think you guys will be asking like that though. Okay, cool. But again, there's not much to do with the mids, right? You guys just hydrolyze them. Right, you either hydrolyze them or you reduce them. That's about it, right? They're not much fun there. Okay, cool. All right, moving on to H, again, another cycle. Don't worry, cycle with cycles, just cut that derivative bond. Right. I guess I guess there's one exception to that. So we'll go over after this. But in this case, right, we'll make this species here. We're using dibble. So this turns into an aldehyde. This will be an alcohol. Just keep in mind with this one, I did sneak in an enol, which you guys might remember or might not. This will be like the 4 out of 5 answer. The actual total answer would be this here. Right. It would tautomerize into a ketone. So you to get this oxoaldehyde is what you would get. Okay. Cool. But again, I mean, this could have been really anything. Imagine if I did lithium aluminum hydride, right? That would just, instead of giving us oh, actually, this would be interesting. So we would get to here, right? So we would get to the aldehyde. And then again, the aldehyde would reduce again. But keep in mind that not only do aldehydes reduce in this condition, right? So do ketones. So the ketone would reduce here too. So you'd actually get a diol. What is going on? Okay, there we go. You'd actually get nope, that's not what I wanted to do. There we go. I guess I just got to do that. Okay, cool. So you'd actually get the diol here. So lithium hydride, this is another one of those, like, you have to think about it, right? It would reduce everything. Dibble would not reduce everything though, right? It would only reduce the ester. Let's say that I did, I guess and then the other way to think about this is, what if instead I did that organometallic on the other page, right? This one here. Again, that would give us this ketone here and this ketone, but both these ketones would then reduce again. Right, we get this symmetric alcohol here, and then this would only add 1, so it wouldn't be symmetric, but it would still be an alcohol. Right. So look at that. This gets a little, you got to think a little bit, right, with some of these. So it's good to see these kind of practices. Okay. So one thing I mentioned was that, sometimes you won't cut that derivative bond. So what was that example? Let's say I turn this into an amide, right? Amides would make this a little difficult. Well, not too difficult, right? It's just that lithium hydride just erases that carbonyl bond. So it's not that you're breaking open anything. You're just doing a carbonyl reduction there. Okay, cool. All right. So look at that. I mean, for each of these, we've done at least 3 of them. So we were always in the 20s in terms of how many reactions we've done on this one exam alone. And we still have 2 more, right? Cool. All right. Acylating agent. We have an anhydride, and we have now a nucleophile, or a double nucleophile. We have a nitrogen and we have an oxygen. So this is a great question to ask, and it really makes you think, right? Again, acylating agents will throw their acyl group at anything. So this could have also just been a chloride. It would not have mattered, right? All that could have been a chloride there, or all this could have been a chloride. It would not have mattered, right? But if I have this propanoic anhydride and we have this aminophenol, right? Where does it go? Remember, general rule of thumb, right? In terms of better nucleophiles, amines tend to win, right? So long as the amine has a hydrogen. So a couple of you are probably, like, oh, wait a minute, you just added something at the end there and made this a little more complicated. So what did I mean by amines usually win as long as they have hydrogens? Well, if you consider our 2 common bases, which are pyridines and TEA, or triethylamines, both of these are nitrogens that don't have hydrogens. So why are we never worried that these guys will compete with other nucleophiles like alcohols and carboxylic acids? It's because if I were to even draw the acylation product, right, of either of these, so I'll do pyridine, right? Notice how I have this cationic nitrogen because there's 4 bonds to nitrogen, but there's no proton to relieve it, right? Usually in a situation like this, like let's say with ammonia, right, we just deprotonate the ammonia, right, the nitrogen, and we get, a very stable product. In this case though, right, in the case of TEA and pyridine, there's no possibility. So if you ever have a nitrogen with no protons, that's not a good nucleophile, right? That's not going to acylate at all. So there are cases where that can be something you consider. Like, for example, what if I just added onto here, right, and NR3? So like a diethylamine, right? Or actually one of the strongest bases that you can use, actually a variant, let's say a variant of the strongest base that you can use is this. The pyridine version of this is a strong base, but I mean, I'm just trying to show you guys something here, right? If you wanted to acylate this, right, it would always go on the NH2 and never on the N-dimethyl. Okay. So, oh, actually, no, this is a thing, right? NN dimethyl aniline. Never mind. I'm just being stupid. You actually use this. I forgot. I was confusing it with the pyridine. So this is DMAP. DMAP has a version of this, NN diethyl pyridine. And then there is an aniline version of this too. Okay, cool. All right. So how could this have changed? Not much, right? You could have, I guess what you could have done here was, oh, actually, this would be an interesting question. So we could have changed this with an acyl halide, and again, the reaction would have always been here. We could have also changed this with an ester too, right? That also wouldn't have really changed anything, right? So we could have used a lot of derivatives here, because the whole point is that we're going to always attack on the amine, right? Alcohol never really goes at one equivalent. Cool. All right. On to the last one. So it looks like we're making an ester here. So I'll put CH3 here. And then we're doing excess organometallic. Remember, any derivative, you got organometallic and excess, you're making the symmetric alcohol, symmetric tertiary alcohol. So that's the methyl that was there before. And then I can add 2 of these butyls, and I get that symmetric tertiary alcohol. Okay, cool. How could this have changed? Maybe I did dibble instead. I get an aldehyde. Maybe I do transesterification, I guess. I don't know why you'd want to do that. But I guess you could have done that. Transesterification got to there, right? So cool. All right, so that's the predicted products. And again, big point there is that, yes, I had 10 problems on the page, but look at how I made them 30. I made it 30 by just trying different things. I know some of you might be a little uncomfortable with that, because you might be thinking, oh, what if I do a reaction that doesn't work, right? Well, that's what the Discord's for, right? That's what Piazza's for. That's what office hours are for, right? Do these reactions and ask people, does this work, right? If you're not confident in yourself, just ask someone else. And you guys always know where to find me, right? To ask me a question. I'm always willing to help. Okay, cool. All right. So moving on to mechanisms. For the most part, I mean, I know the biggest issue with people is that there's a lot of them. So I do have a couple tips here that might help you guys. You really shouldn't. I mean, I know that there's so many reactions on these 4 pages, but you really shouldn't be knowing. You shouldn't be memorizing all of them. You should be memorizing, or at least understanding, the key components of most of them, and you can get a lot of them out of the way. For example, acyl halide and anhydride reactions all pretty much proceed the same way, right? A majority of these use protic nucleophiles because they are so activated they don't need conjugate bases. But a lot of these proceed with the attack on the acyl derivative, right? And usually this acyl derivative is so activated, right? And halides are so activated that we get an instant departure of the Cl group, right? Or the anhydride group, for example. And then because this was protic, right, that Cl will just pick up a proton, right? So look at that. I just described 80–90% of acyl halide reactions just with this one set of arrows, because that's how all of them proceed, right? The only way this really changes is if you use something like a Gilman, or sorry, or organometallic, where it adds again. So this would just add one more time, right? That's how we get the symmetric alcohol here, right? But other than that, I mean, this reaction mechanism is how all of them proceed, whether it's water, alcohol, amine, it's all the same, right? The only thing that changes if, let's say, I used an OH minus, or I used an RO minus, right? These don't need that last depronation step. But don't waste your time writing out all these reactions here. Like, how many arrows is this? 1, 2, 3, 4, 5, 6, 7, 8. I think like 8 arrows on this, if I counted this right, 8 or 9 arrows. Don't write 9 reactions down. You just write one mechanism, and that just described 2 sets of these, right? It described acyl halides and anhydrides. So there you have it. There you have it. That's all you really need to know there. When it comes to esters and amides, right, we do have acid and base catalysis, but for the most part, these guys tend to follow the same patterns. So let's say that I'm doing a transesterification, right, in acid, right? How does this work, right? Well, always in an acidic medium, you protonate. And once you protonate, you have enough electrophilicity to attack, right? Acid is all about proton transfers. So for the sake of this video, I will be drawing out the full proton transfers, because that is what you want. That's what you're expected to do on the exams, because that's how it happens in real life, right? You will get a solvent transfer. You won't get an intramolecular transfer like a lot of you like to draw, right? So this will go out and seek a proton. Okay, so this is the proton transfer step. But once we've activated the group to leave, right? Well, now it's just going to leave, right? It's going to departure. And so we'll have initially a protonated ester, and then something in solution will just pick this up, probably even that alcohol that just left. Right, so that will go ahead and pop this off. Get the ester, okay? And that is your acidic medium catalyzed reaction. So, I'll give you guys a little trick here. I was actually tutoring someone, and I kind of was riffing on the spot. I was just kind of spitting some bars, and I just kind of wrote the letters down of what each, like the first letter of the word that I describe each step with. So protonation, attack, proton transfer, and then elimination, and then deprotonation. And this actually, when you put it together, makes a word or something that you can, vocalize. It makes peptide. So protonation, attack, proton transfer, elimination, deprotonation. I think it's kind of funny, and if you need something like that, you can. But this is what acid mechanisms do, right? Is that's basically what they follow. And guess what? If I wrote this question as carboxylic acid esterifying an acid, guess what? It's the exact same reaction. Nothing changes. Exactly the same arrows. So by knowing one acidic mechanism, you know all of them essentially. The only one that I'll say is kind of different is the nitrile, because nitriles aren't acyl derivatives, so it's slightly different. But when we look at it, it's pretty much the same. So don't write all of them, just write one if you can't remember it, and you know all of them, right? So it's always protonation, attack, proton transfer, elimination, and then deprotonation. Okay. Base is super simple. Base is like probably the best reaction on the planet. Let's say that I have an amide this time, and I'm doing like a hydrolysis, right? Which, hey, guess what? Nothing I said was specific to the ester or the acid. It works for the amide too. This is how the amide reaction would look too. But let's say I have this hydroxide here, right? Bases are always strong enough to attack, and guess what? They just eliminate. So they're super, super quick, these mechanisms. It's just that if you're doing a hydrolysis, the driving force of the hydrolysis is this deprotonation, right? That's why we're even allowed to kick off that NH- in the first place. So we get this here. Okay, so look at that. Usually with bases, if it's a hydrolysis, basic hydrolysis, you do the deprotonation at the end. But if it's like an ester transesterification and base, you just add and you eliminate. That's it. That's all there is to it. It's so simple. It's so easy, right? So look at that. 2 mechanisms on this page we just did together in 5 minutes. Now describe how like half the reactions you need to know. Okay. Now, obviously, there are some oddball reactions, like, for example, the SOCl2 reaction. That's not something that follows a common pattern, which that's okay. I'll do it on the screen right now, just to show you how fast you want to get to be able to do it, or ways to think about it, right? But it's like you're protonating, right? This is kind of like a acidic condition, in the sense that you're protonating. It's like you're protonating the carbonyl with a big sulfur proton, right? Actually, in certain fields, it's kind of accepted that silicon is like a big proton, but that's a different discussion for a different day. That Cl we kicked off now is invited back in, right? And now that's invited back in, we've set up our molecule. And here's a cool little thing you can do if you want to impress your grader. Show them that you're studying outside of the book, or show them that you're different than everyone else. But this chlorine can attack here. This can go here. This can go here. So chlorine there, by the way. And out you get is your chloride, your SO2, and your HCl, right? So the driving force of this reaction is that, yes, the chlorine is still a better leaving group, but once the SO2 leaves as a gas, it never reverses back. Okay, so that's the driving force, is that SO2 leaves as a gas, it will never go back. So we're sort of tricked the molecule into making the acyl halide. Okay, but if something like this is bothering you, look, I've condensed it into a way that you can just do it in a couple arrows, right? In a couple steps, you can write this in your note card, right? This is note card real estate right here, right? Same thing with the PBr3 reaction, right? PBr3 reaction is almost exactly the same as this, right? It does these 2 steps the same. Let me see if I think you can still do the same little cycle thing that I did. OPBr. Yeah, you can still do the same thing, right? This will just attack here. And then this goes here, this goes here, right? The only difference is that instead of making a gas, the driving force of this reaction is the PO double bond. So for reasons that you guys don't really understand, PO is just a very, very good double bond. P and O love making bonds. I mean, you guys actually do understand this. That was the driving force of the Wittig. You guys remember that reaction, right? It was forming this bond here, and then it kind of collapsing into the triphenylphosphine, right? Cool. Anyways, so either if that makes you uncomfortable, then write those down. Oddball reaction, right? Another oddball type reaction mechanism would be like the Hoffman, right? A lot of people have a hard time with that one. My only advice, I think most people understand the arrows on this. I don't really have much tips on it other than to write it down. But when you get to this step here, when you're doing the crazy rearrangement part, I know a lot of people get confused with the arrows, which is fine. You're just, I mean, you have a note card, so you can write this down. You can always do the arrows for the attack. So it's like the R pushes off the bromide and the Malone pair pushes back. Always the result of this is you replace everything here. So everything connected to R just turns into NCO. So it doesn't, you don't have to do any crazy gymnastics or crazy mind Jedi tricks to figure out what should go there. It's always just going to collapse into that, right? And then now water, if there's water in solution or whatever nucleophiles in solution can capture this, right? That little tidbit of information is useful for 1C, by the way, for the Hoffman reaction in 1C. Any nucleophile can capture on this isocyanate, by the way. But anyways, usually it's water. But yeah, that's my little trick there, right? If you're having a hard time with this one, I think most people have a hard time just knowing how to draw the, how to figure out the isocyanate. Super simple. You're just replacing all of this with NCO. Okay. Other than that, just write on the note card, right? Why waste your brain space on this? Same thing with HVZ. I'm not going to talk about HVZ mechanism at all. There's no point. I think if he asks you the question, he'll cut the reaction because it's so long. I think really the most significant part of the reaction is this part here. So if there's anything to write down, it's this part, because the other two parts I think are very, very easy to understand. Why did I do that? This should be a BR. Okay. Cool. So this is like the part of the part of the mechanism that's most important, I think, to understand is getting from here to here, right? We're using the carboxylic acid. So write that mechanism down, right? But I'm not going to bother with it. It's too long. Okay, cool. So that being said, right, hopefully that kind of offers you guys some ideas of mechanisms, right? Yes, there's oddballs, but for the most part, you can condense all the reactions into 3 types. Actually, I guess I forgot to do nitriles, but that's okay, because with nitriles, we can just look at, yeah, there is a nitrile problem on this. So we'll go over it anyways. Okay, cool. So we're doing this in acid. So it's going to follow that peptide if you want to. So protonation. Right, and then attack. So in this case, right, looks like we're making a ring because the oxygen here is the nucleophile, right? But that will give me this here. Or let's do this. Yeah, there we go. Because I've already passed the class, I can do this next thing, which is I'm going to do the proton transfer on the same step, just because I want to. Right? Obviously, you guys should not do this. Yeah, definitely write yours out. I'm just trying to save time here. But that'll then kick out, which will give you the cyclic ester that gets deprotonated by something in solution, right? I'm going to skip that last step, okay? But yeah, look at that. So I mean, if I add in those 2 steps, it would just add in what, like 10 seconds. So once you kind of have an idea of how to do one of them, you have an idea of how to do all of them. You should trust yourselves, right? Don't get bogged down in the details. These mechanisms can't really change, right? They're all pretty much the same. Okay. Cool. All right. I guess a good thing, maybe one thing you guys can do to test yourselves is to do this backwards. Do it in H plus H2O in heat. So a way to write this question, write another type of mechanism question, add on to it, right? So you can try that if you want to. Nitriles, again, yes, I did not show how to do those, but using our tips and tricks, we should be able to hack this out, right? So we talked about in base, the nucleophile is usually good enough to attack. So we'll go ahead and we'll do that. We'll attack here. And what we get out, oops, sorry, will be this here. We have an N minus, right? And remember, N minuses aren't as stable. So in a sense, we can do a bit of a, like a deprotonation transfer, I suppose, right? Where this deprotonates a water, okay? And then something deprotonates this, okay? And once we get to here, right, it may not be super obvious to see, that's totally fine. But this, if I were to go ahead and attack a proton, okay, Look at how many times I just deprotonate and protonate this hydroxide, right? This guy is just a proton transfer machine. But this gives me an amide. And we talked about this, right? Nitriles are just dehydrated amides. So really the hard part of the nitrile is just getting to the amide. But figure out how to get to the amide and then just do a amide hydrolysis, right? In this case, it's what I actually drew on that slide, right? Which is that's that we get to here, go down, kick this off, right? And then we do the deprotonation, right? But look at that, right? Just using what we know, we're able to get to this fairly simply. Yeah, so not too much to stress about there, right? With nitrile, just get to the amide and you'll be fine. Okay, cool. If I wanted to do this in acid, right, I'll just protonate first. And then kind of do the same thing, where I get to the amide. So I hydrate this. OH2 plus, right? Something in solution will deprotonate that guy there. And then I want to go ahead and reprotonate right there. And that will give me the amide. And it's already protonated, so it's the first step. So we have the P part. All we have left is APTAD, right? Which is attack, protonation, attack, proton transfer, elimination, deprotonation. Okay, cool. All right. So that's mechanisms. Hopefully that elucidates on that. Cool. All right, now on to synthesis. So I mentioned that I did want to talk about a little bit of some other type of synthesis before we went on, but this might be a great time to also, when you're doing the exam, is to review your charts, right? Because these charts help you realize what you need to know, what patterns you want to look for synthesis, right? Especially the HVZ patterns that we talked about, those Grignard patterns, the ketone pattern, right? Stuff like that, things to look out for. Okay. But one thing I did want to talk about is that in chapter 19, again, I think the acyl part is easy. The derivative part is easy, figuring that part out. Usually the hard part of 19 is figuring out how to make the carboxylic acid in the first place. So we'll go ahead and we'll use this bromide here. Okay, but there's two pathways usually to make, that you have to usually choose from to make carboxylic acid. I'll just do this. Oops, sorry, water. Right, but one is what I call the CN pathway. Right, that gives you carboxylic acid as such. The other is the MG pathway. So one thing I'd like you guys to notice is not only do I have two different pathways here with two different types of reactions, but look at that bond stereochemistry, right? Look how it doesn't change, or it does or doesn't change, right? Depending on the reaction I use. So one thing to notice there for a predict the products type question, right? But anyways, say we have that, right? Both of these add a carbon. So if you ever recognize you're adding a carbon, these are great ways to go. Totally ways to go. But, if I had to choose one, which one would I choose? So I have developed 3 guidelines that you can use to help you out. Okay. You ask yourself the question of what's the substitution of the bromide? So you ask yourself, what's the substitution of the bromide? You then ask yourself, what is the hybridization of that carbon that the bromide's on? And then the last thing you ask yourself is there any basicity issues? And we'll go over what this means in a second. Okay, cool. But substitution, right? Why does it matter what substitution this carbon is? Is because the CN reaction is SN2, right? This is SN2. So if I'm going to do this reaction, methyl primary, secondary, and tertiary, right? This reaction is only really useful on methyl primary and secondary, right? And even secondary is kind of cutting it, right? Usually secondary is not too great. So if I wanted to do this reaction on tertiary, right, I'd have to use a magnesium. Or if I want the most flexibility on that criteria, I would use a magnesium, right? So magnesium seems to be ahead of this horse race currently. Hybridization is if I'm asking, so I guess I'll write a counterexample here, right? Or when this would matter, right? To do this transformation here, right, you would want to go through the MG synthesis because CN synthesis won't be as efficient. Okay. Hybridization is if I wanted to turn, let's say, this sp2 bromide to this sp2 acid, right? Why might this matter in this reaction? Well, SN2 is an sp3 reaction, right? It's only allowed on sp3 centers. I'm not sure if that was super clearly made and that point was made in 118A and B, but you can't do SN2 on sp2 centers, right? On the other hand, you can transmetallate on sp3 or sp2, right? So magnesium would also win in this case too. Okay. So currently it should feel like magnesium is the winner. And if you should feel like, oh yeah, I should always use magnesium, why are we going through this? Should have just said that. But there is one last criteria here where that's actually going to flip on its head, and that's basicity. Because Cn minus is a weak base and magnesium is a strong base. So why does that matter? Well, let's say that I have the following, this following bromide, right? And I turn this into a magnesium bromide, right? Magnesium bromide is a strong base. So this alcohol proton is actually going to quench it. So if I have OHs or NHs, that's going to quench a green here. And so what you're actually going to get here is this species here, which functionally turns off your reactions. You just ruined it. You just messed up. Okay, there's really no coming back from this. You have to start over. Okay, so how do we, how do we get around this issue? Is you just use the cyanide, right? The cyanide would not have an issue here, and hydrolysis would also not have an issue either. Okay, cool. So for the most part, use magnesium unless there's some basic component, right? That's usually the biggest issue. And in predictive products, consider how stereochemistry would be affected, right? CN is going to invert because of SN2. Transmetallation just inserts, so it's going to stay the same. Retains. Okay, cool. So that's all there is. That's all I wanted to add for the synthesis portion. Okay, but going into this, right? Again, looking at what we have, and maybe we even start with this one so that what we just talked about is fresh. But we can look at this, going into this, right, and consider what you'd want to do. So again, I'm assuming you guys have already done this, so I'll just go ahead right into it and do it. But always the easiest thing you can disconnect are derivatives, right? You can always get rid of derivatives, right? Because you know what derivatives came from, right? They always came from some acyl derivative and a nucleophile. So even before I do carbon count or anything, I can actually instantly do that cut first. And I can say that this alcohol here came from the alcohol in a respective reaction with a derivative. And so the question just becomes, what things can react to make an alcohol, or sorry, an ester, right? And a lot of things can make esters, right? You can use, X could have been an acyl halide, right? It could have been an anhydride, could have been a carboxylic acid, right? It could have been any of these things. So it's really up to you to choose, to pick your poison here. So long as you didn't use the amide, I guess you could have used an ester too, actually. You could have used another ester here. But I if I were you guys, I would generally tend towards like a halide or an anhydride for the reagent here, right? Those are, again, the most reactive, but again, any of these really could have worked. I guess if you wanted to, you could have done this. That would have been kind of funny. Technically it works, but I don't know if I would risk it, right? But yeah. So I'm going to choose the acyl halide here and then add pyridine, because that's usually what you do with acyl halides is add in pyridine, right? Usually pyridine is a solvent in these reactions. It's really good at solvating things. Okay. But any of those could have worked, right? It's totally up to you. So I'll add those pathways in. Let's say you wanted to use carboxylic acid here in a Fischer esterification, right? Or you wanted to do this from an anhydride, right? That would have worked too, right? Anhydride, acyl halide, those are pretty solid options, right? If you choose either one of those two, that's not, you're not gonna get any flack for that. It's really if you did one of these pathways, like like an ester or a carboxylic acid. One thing I guess I didn't really talk about too much is the idea that acyl halides and hydrides being so activated, you could do these in stoichiometric amounts, right? Or usually you would do an excess, but you don't have to, right? Theoretically, just one equivalent of alcohol always reacts with the chloride to give maximum amount of product. When it comes to the acid and the ester, because those are more resilient, you usually have to do a high excess. These reactions rely a lot on Le Chatelier, right? In that you blast it with heat, you put excess reagent, you're really pushing towards the right because the equilibrium constant is around 1. So, on paper, yes, these work, but, typically if I had to choose, I would go with either one. But that's the beauty of synthesis, right? Is as long as you propose something that works, it's fine. But I'm just going to go with the chloride. Okay. So I can already just begin with that. It's the easiest disconnection I can make. But from there, I can do a bit of like housekeeping and notice that, okay, I start with this allylic bromide that has 3 carbons and I end with this alcohol that has 4. So I've added a carbon. So I'm considering here maybe an add carbon situation, right, where I add a carbon to this system. I also have here not a derivative, but a primary alcohol. And once again, you can kind of think about what gave us primary alcohols, right? Hence, it was basically everything. Primary alcohols, if we wanted to associate to a reagent, is lithium aluminum hydride, right? And usually all you're really doing here is you're reacting it with some derivative, right? So again, this could have been a chloride. This could have been an anhydride, could have been an ester. The only thing it couldn't have been is an amide, right? Because an amide would have gave us an amine, not an alcohol. Okay. So in any case, right, any derivative again could have worked here. So I could have done the chloride. And again, chlorides you can only really make one way. That's just SOCl2 and pyridine. So I get the carboxylic acid here. Okay. Could have also been, you know, I could have said, hey, maybe this came from, right? So same reagent conditions there. Maybe this came from the ester, right? Some ester. And again, how can I make esters other than from acyl? I mean, I guess acyl halides, right? And then done that, but I could have made it from the carboxylic acid, right? That would have just been ROH, right? An excess of ROH, H plus in heat, right? That could have worked. But I guess you guys can all kind of see here. I mean, actually, even the carboxylic acid could have made this. So again, you guys can kind of see here, there's a lot of variability here. I'll kind of put quotations around this so you guys can see what it is that I'm like saying is the same here. These three arrows are the same. This one, this, and this one. But you can see there's a lot of variability here. I guess if we wanted to go path of least resistance, or the path that's the shortest, it's to go through the carboxylic acid, right? You can do that reaction there that gets us the primary alcohol. But we, you know, on paper, technically all these routes could have worked, and these are all viable routes that people might try, right? If the carboxylic acid reaction doesn't work very well, right, then the next step is do acyl halide. Acyl halide. If the acyl halide route is too harsh or doesn't work, you could try the ester. So this is what an actual lab scientist would do. And so all these are viable. Cool. Regardless of any of all these, you always go back to the carboxylic acid, because from there, right, it's a matter of, you know, how do I turn this allylic bromide into that? And so again, there's two ways you could have done this, right? You could have done the Mg pathway. Oh, did I? Shoot, I think I'm gonna did I mess that up? Hold up. Oh yeah, I didn't even write this down. My bad. It should have been CO2 and then H plus. Crazy how I'm now recognizing that I didn't do that. I apologize. It's because some of you are probably screaming at the screen. Shoot, I did not know it was gonna erase all my drawings. Do they come back? No, they don't. Okay, shoot. Sorry, give me 1 second. I'll write down most of it. If anything else was needed, you know, you can always just go back in the video and get that down. Okay, but I'm just going with the paths of the lowest count path here, which is just this right now, right? Sorry, my handwriting is getting very bad. Cool. So from here to here, right, I could have done the Mg pathway, or I could have done the cyanide pathway. You guys might be noticing that I'm doing something a little weird here, in that I'm like drawing two discrete arrows. Generally, when it comes to Grignards, you don't make the Grignard and isolate it. You make it and then you react it. So it's okay to put it all on one arrow. The cyanide reaction, though, that is something you would isolate usually, and then hydrolyze. So technically, it is, you can get one less arrow here. I guess you could have also shoved these on the arrow. It doesn't really matter. But there you have it. That's our first synthesis. All we did is a Grignard. We did a add one carbon synthesis of an acid, and then we transformed it a little bit, or acylated at the end. Okay, but that's kind of the ideas you want to take into it, right? Like, how can I make my derivative, right? Did I add any carbons? Imagine if I didn't, right? Imagine if I didn't add any carbons. I just went from here to here, right? Don't just do these reactions because you see them. Right? If I turn this into this, I mean, this is just hydroxide and then Jones, right? You're just turning this into an OH and then jonesing it. So always make sure that you're doing things with intention. Don't just do them for any reason, for whatever reason. Yeah, cool. All right. So that's the first one or second one. That would be easy. Let's do the first one now. So again, we're starting from an alcohol and we're turning it into this alcohol here. I think the number one thing that pops out to me is that this is a symmetric alcohol. And so again, how do I make symmetric alcohols, right? That was usually the reaction of a derivative with a Grignard, so R minus, and that will give me an alcohol with usually these two R groups flanking it and something else. But in this case, right, it looks like all three groups are symmetric. And that's just because the original chain is what I just ended up adding, right? So if I kind of wanted to trace out the original chain, that'd be that. So the new carbons here are this guy and this guy. So those are my Grignards, or my one Grignard, I suppose. Right? It's just going to be this with an Li on it, or an MGBr. I haven't been using MGBr much, so I'll give it some love now. And then water. Okay. But from here, right, again, this could have been any derivative. Right? Any derivative would have done this. I guess if you wanted to, you could do, again, I mean, I like using Cl here, but you could have used OR, you could have used NR2, right? Matter, anhydride would have worked here too. I'll just use the acyl halide, because again, there's only one way to make that. It's just a carboxylic acid. And then again, from here to here, again, don't just willy-nilly do some one add carbon synthesis or do like a CN or MG. You don't add any carbons here. So you just got to do it Jones. Don't overthink it. Okay, cool. So those are our two syntheses. Fairly simple. These are both 3 steps. And you know, the number one thing I want you guys to realize is that, yeah, it's great to have someone write you synthesis problem, right? But one of the best ways to practice these on your own when you don't have access to this is just take a substrate and do a couple of reactions on them, right? Because most syntheses are just 3 reactions. So for example, I mean, what if I just took an ester, like let's say I took this and I said, okay, I want this to be an ester, and I just want to do 3 reactions on it, right? So maybe the first one I do is like a dibble, and then maybe I do NaCN. Okay. And then maybe I do a hydrolysis. Right. So that gives me this alpha hydroxy acid here. Right. And then what you'd want to do, right, once you do those reactions, is kind of erase your intermediates and work your way backwards, or work your way to see how you figure out that I want to go from here to here. Right. What key elements gave away what you wanted to do? Right. I think the number one thing that gives away what I might want to do here is that I have this alpha hydroxy acid. So actually, maybe I might have thought HVZ here. That could have been something. So one thing that'd be nice to write is, okay, if I have an alpha hydroxy acid on your note card, consider that it comes from an HVZ reaction, or consider that it comes from a cyanohydrin, right? These are both things that I can consider. And so what would give away to me one over the other, right, is that, remember, cyanohydrin adds a carbon, right? So this is adding a cyanide, adds a carbon. So when I go from here, this ester, which is about 7 carbons total, to 8 carbons, right? 6, 7, 8. I'm thinking, okay, I added a carbon, so maybe this came from a cyanohydrin. I can also just think about the starting material, right? Like, how in the world would I do HVZ on this? That would be horrendously difficult to do HVZ on this and then it turns to this. Okay, so having these little cues in your note card, that's what they're for, right? Your note cards have these little tricks and tips, like, oh, I can quickly figure this out if I just know, okay, these are 2 things that make my substrate, right? How do I move forward? So I could do something like that. I think one thing I didn't do a lot of is like putting 2 functional groups on here, but we can even do that. Like, let's say that Cl ester example that I was using earlier a lot, right? You could do some pretty cool chemoselective stuff here. Like, for example, maybe I do like, I don't know, something I could do here. Maybe I do a reaction with ethylamine, right? Where is that going to react if there's no heat? There's no heat, that's going to react on the acyl halide, right? And then maybe you know what'd be cool here, actually? Let's do a lithium aluminum hydride, right? So remember, for the amine, that means getting rid of the carbonyl. For the ester, that means turning it into an alcohol, right? And then maybe I cap that alcohol, or, oh, sorry, let's actually do this. Let's do this diethylamine, and you guys will see why I'm doing this in a second, right? All of this is just to inspire complexity, right? But then let's do that, and look at that, right? So remember, tertiary amines or amines with no protons aren't very looking to react with nucleophiles, but alcohols will. And look at that. Now I have this like really complex product. So then I just think, okay, how do I come about this product here? Right? How do I go from here to here? It looks really crazy. Well, I think what I would look for is, okay, what can I trace? Right? Is the same. And so ring and these carbons are pretty much the same. And when I kind of look at the carbons here, hey, look at that, right? Those guys are reduced. Okay. Well, actually, maybe the first thing that I would do here is, okay, remember how I said we can always get rid of these here? So let's get rid of that first. That's probably the easiest thing to do. Right. So we can get to this amino alcohol. But again, when I kind of trace out the carbons and I look at, what used to be what, look at that. That's reduced, right? I've turned those carbonyls into CH2s. And there's only really one way to do that, right? Get primary alcohols or get amines, right? That's going to be LiAlH4, right? So I have a very clear pathway. I mean, and from there, right? So I know this is going to be an ester simply because it started as one. But now I have this amide here and I can see, oh, I just amidated that acyl chloride. Right. So, just taking substrates and just doing 2-3 reactions on them, maybe even 4, that's a very good helix synthesis, right? It's a very good thing that you can think of and try to do. And I know it's a difficult thing to do, right? Because it's a daunting task, but just got to go through the motions, right? Like, for example, let's say I mentioned nitriles. So like one of the only ways to make ketones, right? So maybe I make a ketone out of it. I guess there's not very many reactions right now we know to do with ketones other than cyanohydrin, right? So I guess you could do that. So yeah, another access to the cyanohydrin, and noticing again that you're adding a carbon. So that's why we want to do that. Okay. Cool. All right. So again, just for the sake of time, we'll just call it there. I mean, again, we have 2 other midterms that we can talk about synthesis a lot of. And I think that these three midterms that I wrote kind of capture a lot of the good things to know. Cool. All right. So working on to explanation. I mean, explanation is really anything that you were told in class to be aware of, to be, to remember is kind of like, not like an exception, but it's a reason why something will work. So the greatest ways to find explanations is whenever you have to write like, oh, this would work, but this wouldn't, right? Or when you would say, oh, okay, so I need to, like, for example, I mean, if we look at this particular example, acid to ester, right? We know that as the Fischer esterification. That works in acid. So this was H plus, right? This would totally work. So why again does this not work in base? Well, remember, bases and acids neutralize, right? So what we would get is the carboxylate. And like we mentioned, carboxylates are very stable. So the best possible answer you could use for this is to say that bases neutralize acids, or bases neutralize carboxylic acids into the carboxylate, and that's very stable. Not very many nucleophiles can destroy this. So that's why this won't work, right? To make this work, you just put it in acid. Okay. But there's so many different things that we could use. I mean, you'll see it on the other ones too. Another good one is like, let's say that I started with the ester and I asked you, again, why doesn't this go to the anhydride if I try to, right? Again, you're asking, in this case, you're asking for the system to give up a stronger base in the tetrahedral as opposed to the weaker base, when the tendency is always to give up the weaker base. Okay, so that's why this wouldn't work. To make this work, you'd use like an acyl halide, right? That would be the answer there, right? Oh, actually, one that you guys can think about is, why wouldn't this trans esterification work? So this is actually a bit of a difficult one. You've really got to think about this one. Or maybe you don't have to really think too hard. But if you just use what I just said, it kind of goes away the answer. Why won't this trans esterification work? And the answer is because, again, when you think about the tetrahedral intermediate and what's being given up, right? You always want to give up the weaker base, or the weaker base or the stronger acid, right? If I consider the acidity of these two groups, so if I just kind of isolate these as O minus like this and O minus like that, consider why this O minus is a weaker base, right? Why is this phenoxide better than this alkoxide? Well, because that charge can resonate. So it's actually really hard to make, I mean, this is the reason why we never use esters to make those phenol esters in 118B. We didn't really explain why, but now you guys understand. It's because the weaker base will always be given away. So this will never work. You'd have to use an acyl chloride for this for sure. You can also apply this to other substrate types, like things outside the scope of the class. So like, for example, why can't I turn this ester into this thioester, right? Why is the thioester unable to be formed from the ester? It's kind of the same idea here, right? It's thioester, if I put a minus on that, that's more stable than the alkoxide. Okay, so look at how many ways we can just write a question. I guess I wrote the same question 3 times, but look at the substrate scope, right? Look at how much you can cover just by knowing that one piece of information. Okay, cool. There's a bunch of explanation questions. I mainly use your study guide to write these, so use your study guide and think about what works and what doesn't. The other 2 exams, that I made have very good examples of these. Cool. All right. General knowledge sentences. Just read them out. Again, I use your study guide for this, so just look for terms in there that might fit. For example, very stable anion and resistant to most nucleophiles. We just said this. That was the carboxylate anion, right? And it's usually very stable unless there is, it's resistant to most things unless it's like something super strong like a lithium aluminum hydride. Right? That was the one thing that can break through it. Okay, that's that there. Reacting primary amide with Br2 OH-, that's the Hoffman. So we're forming an isocyanate, right? Carbamic acid decomposes in water to form the primary amine. So how do I write these? How did I write these problems? I literally just opened your study sheet. I looked at the terms and concepts to know, and I thought about sentences that made those terms true. That's it. That's all I did. So go back in your notes, go back in your study guide, think about words you can say, or words you need to know, and sentences you can say that are true about them. That's how you study vocab. That's literally it. That's how I made all 6 of the ones that I made for these exams. Cool. All right. Okay, we're actually not too bad on time. I think we just hit an hour and a half right now. So I don't want to spend too much more time. This one will probably hit 2 hours, not gonna lie, but the other 2 won't. I'll guarantee that right now. The other 2 will not. Okay, so derivative trends, right? Circle the molecule that reacts the fastest with water. Okay, so derivative trends, if you know one of them, you know all of them. Okay. So I'll go ahead and draw out the derivatives here. All right. So I have the derivatives here. And like I said, if you know one of them, you know all of them. And that one is the resonance trend. So when consider resonance, how much resonance donation we have from these X groups, right? Nitrogen donates the most. I know because it's nitrogen, right? Nitrogen always gives up electrons. Chlorine donates the least. So resonance trend goes this way. So just off this one trend, we can build off every other single trend we need to know for this class. Primarily, if that nitrogen is donating the most, it's got no business leaving, right? On the other hand, chlorine doesn't donate at all. So leaving group ability or reactivity is dictated by resonance, right? How much does that group participate? If I draw the resonance forms that these arrows would give us. Sorry, sometimes I get so deep in thought in drawing, like I'm such a, like I tried to multitask there and my brain didn't let me, but anyways, if I draw the resonance forms, I get these. Again, acyl halide, actually, if I were to give you one, the one that some people kind of accept is a resonance form is this one here. Okay, is this ion pairing here, which is a little interesting. Okay, we can talk a little bit about these resonance forms, right? Primarily, there's these O minuses and 3 of them. We know O minuses to be bases. So if I were to consider how basic these carbonyls were, right, I could talk about how strong that O minus character is in each of these derivatives, right? The more you resonate, the more O minus you have. So the amide, which resonates the most, will have the most basicity. So because it has the most O minus character. And on the other end of that, right, is going to be acidity. So when we think of acidity, we're thinking alpha acidity, right? So how does this work? So let's say I have a minus here, right? The enolate anion. Remember, the enolates want to resonate. That's what stabilizes them. But if you have the enolate in this resonance form, that enolate is locked, right? Because the competing, or the X group is competing for resonance. Okay, so this X group here competes in resonance with the enolate. And if it competes a lot, it's going to destabilize the enolate even more. So this is one of those weird things where more resonance equals destabilization, but it's because it's more resonance of the X group, right? If the X group resonates, it destabilizes this enolate by not letting it resonate, right? Sorry, I had to sneeze. So yeah, so the more of this anionic form that we have of these O minuses, right, the more destabilization we have of this enolate anion. So acidity increases with the acyl chloride. It's also the only species with a cation, right? This cation here, so it's definitely the most acidic. Okay. We could also talk about bond length, right? So you guys hopefully talked about this in class. The amide has the longest carbonyl bond length, but Bl here, right? Because it has the most single bond character in its carbonyl, right? It has the most resonance in there. So that's the longest. So in the IR, this shows up about 1680, right? Look at the acyl chloride. That's the triple bond almost. So it's gonna be really, really high up. It's gonna be close to 2000, right? It's gonna be 1810. Okay. And anhydride tends to have two peaks, one that's really high, one that's really low. Okay. And this guy is sort of in the middle somewhere, 1740-ish. Okay. So that's that trend there. On the other hand, right, if we're resonating a whole bunch, then we have a bunch of this double bond character in the CX bond. So you can imagine that the CX bond, I mean, think about it, right? We're saying that the CX bond is super short in the amide because it resonates. It's super long in the acyl halide because it's an ion pair. It's almost departed, right? The Cl minus. So this bond like this super long. Okay. I mean, there's so many trends you could take out of this, right? I mean, all of it just depends on, your understanding of resonance and how that might affect the trend. So for example, if you're asked about boiling point, right? I mean, you can even take a much more practical approach to this. Who would boil at the highest temperature? That would be the amide, right? And that's just because, I mean, if you think practically, we are amides. If we didn't have a high boiling point, we'd just be pools of water, right? Acyl halides boil the quickest, I suppose. Cool. Now, let's say that I had an aldehyde and a ketone. Where would these usually go? It's a little difficult to kind of place them. It kind of depends on who you ask, right? Some people might say the aldehyde is about the same as an anhydride, or it's a little bit more. Kind of the consensus is that ketones are pretty trash. They're always going to be below anhydride. So this is a tough call to make, honestly, the aldehyde and the anhydride. If I had to, I would put the anhydride first, probably just because it's more electron withdrawn. So you could kind of sneak it a little bit over here, I suppose, but it's a little bit of a toss-up. Aldehydes are a little too electrophilic, but yeah. So if you wanted to put them somewhere, they'd go around here. And for the most part, the trends are about the same. The trends are about the same. So especially the acidity trend is about the same. Right, if you consider pKa values. So I don't know if you need to know these actually, but this would be around like 15. This one doesn't really have a value. This would be around like 17, 20, 25, 30. Right. Nitrile is a little interesting. Nitrile actually sneaks in with the amide, with the ester here, at around 25. So when we talk about ester enolates in chapter 23, nitriles will they'll show up again. Cool. All right. So this is the trends for the most part. It's all you really need to know. If there's any other trends, I'll talk about them in their respective videos. I think the acidity trend may need a little more talk to, because there is the carboxylic acid, which I guess technically is the most acidic thing, right? Because that's at 5. This proton here is at 5, right? Amide kind of follows up very close. It's about the same as an acyl halide, actually, right? Because I told you it's about like 15-ish, right? So these guys kind of sneak in a little bit at the ends there. Yeah, that's about it. Cool. So this should cover, if anything, if you need it. So if you need to, pause and you can write this down, but yeah, cool. Anyways, this problem was just asking about reaction fastest with water. So if I consider that, I mean, we have an acid which doesn't have any reaction with water, so get that out of the way. Amides are the most resilient next to the nitrile, so that's definitely out of the way. Oh, this should have been a ketone. Oops, not an aldehyde. This is a tough call to make, so I apologize. I should not have done that. But we'll go with the anhydride just because it's a derivative. Technically, these are about the same though. Should have been a ketone. That's what I want this to be. So I did not proof this well enough. I apologize. Cool. All right. So just the fast reaction with the nucleophile there. That's all you need to know. Cool. All right. When it comes to benzoic acid trends, again, if you know one trend, you know them all. Right. When we think of benzoic acids, right, it's these carboxylates, right? How stable are they? Right. Generally, the idea is what charge do you have in them? So we can have EDGs or EWGs. Okay. EDGs put a positive, EWGs put a minus here. So the question is what charge pairing is more stable, minus minus or plus minus. And in every single case for acidity, it's always the plus minus. So these guys are highly acidic. These guys are not that acidic. Okay. If I were to consider different positionings, which ones are better than others, recall that an EWG, if it has an effect on a ring, or if an EDG has an effect, it's always ortho and para. So it's at these positions here that it has an effect. Okay. So having an EWG with an acid that's ortho and para is always going to be the best combination, because you can see that it puts the minus right on that carboxylate, because the minimum distance between the minus and the positive, right? And that's a stabilizing interaction. So all these positions, ortho and para, so ortho and para usually are better than meta, because if, let's say I had an acid here, right, where these are meta to each other, right? Well, guess what? Now that they're meta to each other, you don't have that positive minus interaction as well. I mean, yes, the ring is positive, but it could be better, you know? So meta is always going to be worse. Between ortho and para, right, both of these, again, have the same resonance interaction and that they have the positive. So the only thing that's different is that there is an inductive pull, right? And that's closer when you're ortho. So in that case, right, ortho is better than para is better than meta. Okay, so that's your EW trend. EDG is just going to be the opposite, right? If I have minuses now, in what world do I want the carboxylate right next door to the EDG, or right across from it? Why do I want that resonance connection? It's a really bad interaction there, right? As opposed to being meta, where we avoid that minus-minus interaction. Okay, so meta is now better than ortho and para. And again, between ortho and para, right, EDGs usually have an inductive interaction. They usually have some inductive interaction. So ortho is better than para. So we have opium. So that's how I remember this one, opium. And then we have MOP, right? And MOP is really easy to remember. Okay, cool. All right. So that should be about all you really need to know for trends, honestly. It shouldn't be too much other than that. We'll see, I guess, when your practice questions come out, if it's more complicated than that. But remember, EDG is worse than EWG. So get rid of any EDGs. We'll get rid of that because we're looking for most acidic. From there, we have bromides and CF3s. Bromide has a lone pair on it, just like, so the reason why this is EDG is because it has a lone pair next to the ring. So get that out of the way. Bromides are withdrawing, but they have a lone pair next to the ring. So they're kind of like they're like the worst withdrawing group. So this one automatically loses as well. So it's between the ortho meta CF3s and the ortho para CF3. So based on what we just talked about, it seems that we'd want to gravitate towards this answer here. Okay. Cool. All right. I guess, really the trends that I highlighted are for resonance groups. So to make this question a bit better, NO2s should be put here, right? Or any resonance withdrawing group. Technically, the inductive ones are a little different, but it's whatever. Cool. All right. Figure it out. Nomenclature is your guys' thing, not mine. Cool. Spectroscopy. So I wasn't sure if it was going to be matching or if it was going to be an actual spec question. So we'll do both. The matching questions, I hope it's this, because you can do these in less than a minute. And I really do mean less than a minute. Because I imagine a lot of you, what you do is you sit down and you start looking at the hydrogens and you start thinking about which ones have which multiplicity, blah, 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 blah. Don't do that, right? What I want you guys to do anytime you get these is you just want to look at it and use your third eye, your OChem sense, right? Use your theory for electron withdrawing and which hydrogens show up where to kind of guide you through most of these. Just a quick reminder, just because I do want to end this off within 10 minutes. How can we do these, or what were the trends, right, that we need to know? Generally speaking, 5 is the cutoff for sp2 carbons and sp3 carbons. So if there is like electronegative atoms, right, they're kind of in their own group here, but generally going this way increases with electronegativity, right? And this way as well. Okay. Some notable areas to know is 5 to 6 is alkenes, usually, or 5 to 7 is like C double bond C. Like the rest of this 8 to like a 9, right? That was the benzene area. Like if there's hydrogens here, right? So these aryl protons. Remember, carboxylic acid protons show up around 12. So ding, ding, ding. We just figured out what that is. Aldehyde protons, they show up around 9. So actually that should have been not there. It should be around here. Right? These aldehyde protons show up around 9. Right? If I have something that is next to like, it's an sp3 carbon with an alcohol, or like oxygen, nitrogen, a halide, right? That usually tends to show up around this region here. So this is like if I had like an OH or an NH or an X8 or an X here. right? And then remember, these OH and NH protons, they show up anywhere, but they show up broad. So you don't have to really guess about which ones they are. They're the broad ones. Okay. Everything else is usually very boring and you can just kind of guess. Okay. So that's like the quick and easy trends. I can't go through all these. So if you need to, just watch the NMR video I made, just the first part where it goes over what is where. That's that. Oh, I guess the only other thing I could mention is usually about 1.5 to 3 is alpha to some EWG. So like alpha to like a ketone, right? Or alpha to like a nitrile. That's where that would show up. Or like alpha to like just an alkene, right? That's where that would show up. So again, if you need to watch the video, just that first part to get all those down. And then in the CNMR, if you needed it, actually we'll do this in the next one because that's where this is important. CNMR is not really important here. But anyways, right, I just want you guys to use OChem sense, right? Don't overthink it. For example, we just said that alkenes show up around 5 to 6, and I do see some proton activity, you know, in this area here, right? It's not totally 5 to 6, but it is within that area, right? And I do see an alkene in here, so I imagine that B and C are going to be these two protons here, right? Because again, that's our alkene area. Which one is B and which one's C? So you can do the really, you know, cheesy way of just counting the neighbors and figuring it out, but we can also just use OChem sense, right? If I kind of draw out what I have here, I have a ketone or a carbonyl next to an alkene. That's an enone. And you guys remember in enone chemistry, there was 2 positions where we attacked. We attacked at the carbonyl and we attacked at the beta carbon. So for attacking, that means that we have delta positives at these positions, okay? Delta positives indicate de-shielding, right? That's where things are de-shielded. They're gonna be more to the left, right? If there is a negative somewhere, it's gonna be more to the right. So if there's positives here, there's an implied negative here, right? Because charges like to be opposite. Anyways, so we can actually tell B and C which one is which, because if C is that beta carbon, it should be positive, it should be de-shielded, it should be more to the left. So this is C. And then B is going to be on that more shielded carbon there. It's going to be B. Okay, so look at that. Just using chemical intuition, right? Already got these 2 there. Again, we figured out 12. That's always carboxylic proton, so that's A. All that's left is now D and E. And think about it. Who's closer to the nitrile, the electron withdrawing group? It's D. So I didn't even look at multiplicity. I just thought about chemical intuition and I got all of those. Okay. Now, you're probably not going to get something as easy as this, right? This is only 5 boxes, but if it's 6, 7, 8 boxes, again, all you do is chemical intuition and you'll be fine. That NMR document that I made has a lot more challenging structures that you can do that with and should get you through most of them. Cool. So let's actually do the NMR problem, the one that will take longer. Again, always start with your DOU. So 11 times 2 is 22 plus 2 is 24. Minus 12 hydrogens is 12 divided by 2, which is 6. So 6 degrees. If anytime you have higher than 4, look for see if there's a benzene. I see benzene activity. So 4 degrees are going into a benzene ring here. Bonus points if you realize that that 2H tells you that it's para. Okay. Where are my last 2 going into? Well, I could use the IR, but easier thing to use is the CNMR, right? In the CNMR, 160 to 180 is your acyl derivative region. So think halides, anhydrides, esters, amides, and carboxylic acids. 190 to 210 is the ketones and aldehydes. So if those guys were there, you can use that. 100 to about 150 is C double bond C. Sometimes nitrile can sneak in here as well. And that's usually all you need to know for the CNMR. Yeah. So I'm just looking for 2 more derivatives. I mean, I know there's alkenes here just because I have the benzene, right? So I'm not too worried there. These 2 lines though that are in the acyl derivative region tell me that I've got to have some kind of derivative, and there's 2 lines there, so there's 2 derivatives. So I know that there's gonna be 2 derivatives in this. So if I go in my fragments box, I can again write my benzene fragment, and then I have 2 derivatives. I just got to figure out what they are. One really cheesy way you can figure this out is you can look at the formula. If there's any halides or amines, right, that tells you that there's a amide or an ester, or amide or an acyl halide usually, right? But I don't see either, so I know that they can't. So I guess it's better to say that if they're not there, you know that they can't be those. So no halide, can't be acyl bromide. No nitrogen, can't be amide. So it's either ester, acid, or anhydride. Acid is super simple. Look for the acid proton in the NMR, and we do see it. So we know one of these is an acid, right? Anhydride is a bit difficult usually. I mean, you usually need a lot of oxygens, but we can prove that this isn't an anhydride because 2 oxygens are being used already. So there's only 2 oxygens left. And I would need 3 for an anhydride at least. So it can't be that there's an anhydride other than this carboxylic acid. So it's going to be carboxylic acid and ester. Okay. So I've got now these 3 fragments here. And I can start to build. Again, I've already kind of resolved these guys here. I'm just keeping track. So I'll get rid of those. I don't need to worry about that. And I've already figured this out. I don't need to worry about that. All I have left is a 2H, 2H, and a 3H. That 2H is super, super high up. I mean, it's past 5. So if I had to choose between what atom it's got to be next to, whether it's next to carbons, or an oxygen, it's always going next to the oxygen, right? So I can almost even start with the ester and say that there is a 2H here for sure, right? It's a singlet, so it has 0 neighbors. So whatever is here has got to be 0 neighbors, and obviously the oxygen is 0 neighbors. Okay, so that's this here. The fact that it's super high up means that it's got to be next to an oxygen and something else that's electronegative. So I guess you could choose to put, if you wanted to, the carboxylic acid here. That looks a little weird though. Maybe I like this better, right? So actually, yeah. So how can we reconcile? Because maybe Dr. Helix might go for something weird, right? Let's say that I do choose to put the carboxylic acid here, something like that. Yeah, let's keep this fragment on the side for a second, because I guess we should have good deductive skills, right? How do you know which is which? I could also go with there being the the benzene ring here too. Oops, sorry. It should be this. Right, cool. All right. All that's left now is a 2H and a 3H here. So we'll have a 2H quartet, a 3H triplet. The 2H quartet, it's going to be next to a carbonyl. Okay. It's a little bit low though. So I guess there's sort of two possibilities here. Either we've got the 2H next to this guy here. So next to the ester, right? Because that's a carbonyl. Or I've got it next to this carboxylic acid here. Right. So I've got this 2H here. Okay. So where would this go? Well, first off, the 2H is a quartet, so it's next to the 3H, so it's got to be with this. If I put the 2H and the 3H there, hopefully you guys can see why this wouldn't work, right? The ethyl piece here kind of terminates the molecule before I can connect it to this piece here. So it doesn't make sense that the ethyl goes next to the acid. It couldn't go there, right? So it's got to be that the ethyl goes next to the ester, because it does terminate this side, but we still have this piece here that we can connect here. So we can go ahead and connect these 2 pieces here like that. Or, right, what we could do is we could, well, I guess now this kind of solves it, right? Because we could, actually, I guess, hold on, we could do this and then put like an ethyl here. We could do that. I mean, hopefully you guys can see why this one feels a bit more comfortable. Something weird like this, I wouldn't really bank on it. It's a little bit weird. I would say if you can make 2 structures and one feels better, I would go with the better feeling one. I can see arguments made for both of these though. Like technically this could kind of work. I can see how that could kind of work. So to me, it's a little, wonky looking. Okay, cool. All right. Anyways, we want a mostly correct answer, if not the most correct answer, right? So cool. All right. So that's midterm 1. Hopefully that walkthrough made sense and helped you see how I think with these. Again, biggest thing to take away from this is how we can take one prex exam and turn it into basically a million with all these questions. I promise you guys, I know this was 2 hours. Promise you guys the next one won't be. I'll just go through the problems and do, I will do extra stuff, but we won't. I think like 30, 45 minutes was into just going over review. So that won't be in the other 2. So those would be a lot shorter. Again, if you're crunched for time, make sure to watch 1B as well. 1C, it's okay if you don't watch it, but 1B and 1A are, I would say, if you want to do well on the exam and you don't know anything, best way to do that is to watch 1A, 1B. Okay, cool. All right, if you guys have any questions, let me know. You guys have a good one. See ya.